Now that we can make electrochemical cells, we can start talking about them in their standard reduction potentials. When you have a standard reduction reaction, that's going to be a half reaction like we've seen in previous pages. But those half reactions have a voltage assigned to them, and those voltages are measured either at 1 atmosphere for gases or at 1 molar for aqueous solutes. So the voltage is measured. Now we have these voltages and they are tabulated for you. If I scroll down, you can see them, and they are tabulated as half reactions. These are all reduction reactions. And you see over here on the right, we have this standard electron potential. We have the standard potential of E0. Now on this table, we have an awful lot of half reactions. These half reactions are in order by decreasing order of their standard electron potential. When comparing two half reactions, the half reaction with the greater reduction potential is most likely to be the cathode in a spontaneous cell. A galvanic cell is a spontaneous cell. It's one that does not require additional electricity to be applied in order to make the reaction occur. A non-spontaneous cell is going to be something called an electrolytic cell. That's where you have to add additional electricity in order to get the reactions to occur. Now, all half reactions are reversible. To get the oxidation reaction, you would flip the half reactions so that the reactants become the products and the products become the reactants. And at that point, the sign of the standard reduction potential would also change. Now we can calculate the voltage of a cell by using these standard reduction potentials. So for example, if we're given this cell, what's the standard cell potential for a galvanic cell? And because it's galvanic, we know that the cathode will consist of the item that has the greater reduction potential. We can identify both the oxidizing and the reducing agents, and we can calculate the E cell. Now the E cell is going to be equal to the E0 of the cathode minus the E0 of the anode. Now these voltages will be found directly on that table. So when I have the E0 of the cathode, the E0 of the anode, I have to figure out what's going to be the anode and what's going to be the cathode. So first thing I'm going to do is write out these half reactions. So I have gold with a 3+ charge reacting with 3 electrons to form solid gold. And that's what this part shows me. Now I can create the other half reaction like this. Now, unlike with balancing a redox reaction, the stoichiometric coefficients are not used to scale the voltages. We're just going to read the voltages raw from the table. So I'm going to go back to my table, and I'm going to find gold, and I'm going to find silver. And it might take a little bit of looking, but be patient. So my gold is found, let's see if I can highlight it, right here. This is my gold reaction. And it has an E0, and I'm just going to write that down real quick, of a positive 1.498 volts. Now I'm going to go back and look for my nickel. Nickel is found here. You see it matches the half reaction that I wrote down. Nickel 2 plus 2 electrons reacts to form solid nickel, and it has an E0 of negative 0.257 volts. The greater the standard reduction potential, the more likely that's going to be the cathode. Greatest chance of being reduction. This is going to be my anode. So now I can calculate the E cell by taking the E0 of the cathode and subtracting the E0 of the anode. Now again, when I'm using these E0s, they are raw from the table. I'm using the reduction potentials. Remember, when subtracting a negative, we are actually adding. So the E cell is going to be positive 1.755 volts for this reaction. To take this one step further and put this particular question or this particular situation in cell form, I start with my anode. I declare what it's being oxidized into. I have my salt bridge. I have my cathode anion, phase change, electrode.